So the basics of chapter 1 is introduction to the atmosphere. There's a lot of simple things here, and this is going to get you familiar on some of the concepts that we're going to talk about through later in the semester. And then once we get into chapters 4, 5, 6, right through chapter 11, that's more about weather forecasting. Again, the atmosphere, okay, is the study of all the air around the Earth. And that's what this course is, Introduction to Meteorology. We're going to study all the air around the Earth. We also have the geosphere, which is the solid part of the Earth, and that's geology. And then we're going to be looking at the hydrosphere, study of all the water on Earth. Remember, 97% of the water is in the ocean, and if you wanted to study the oceans, that would be oceanography. That's what we're going to be looking at for storms, tropical systems, hurricanes. We'll get an idea on that as we go throughout the semester. Biosphere is the study of life forms. That's the Earth itself. What are all the life systems on the Earth? And these systems are all a complex group, and they're all inside our atmosphere. So that's one of the things we're going to be looking at. But we're going to be focusing on the atmosphere as we go throughout the rest of the semester. We also have a closed group here, okay? And inside this closed group, we have two sources of energy. One is the sun, okay? The sun, if we didn't have the sun, we'd be much, much colder here on Earth. So as the sun's rays comes in, it hits the Earth's atmosphere and it heats it up. So it heats it coming in and it heats it going out. So the second form here is the heat from the Earth's interior, which comes in from underground. So what we're going to be looking at is how do we heat the Earth? How do we get temperatures in the 90s, 100s, 120s? Okay, as we go throughout the rest of the semester, we'll have a better understanding on how hot an individual day can be. But without the sun, we're not heating up anything. So pretty much the sun heats up everything that we have around us. Okay, one thing we'll look at throughout the semester is the water cycle. We need to have evaporation, condensation, and precipitation. We talk more about this in chapter 4 and chapter 5. That condensation, that's actually clouds. And we'll look at 10 different types of clouds when we talk about chapter 5. So basically what you need to know is that there's water in the atmosphere. There's water vapor. And by volume, it's about 4%. So with that volume of water, it's kind of moving constantly throughout the Earth. It evaporates, it condensates, you have precipitation, and then also you would be looking at snowfall or rainfall. So those are the things that we would definitely look at as we go throughout the semester. Okay, one of the important things that we're going to be looking at is what is the atmosphere made up? Okay, there's two predominant gases, that is nitrogen and oxygen. Nitrogen is number 1, which is about 78%, and oxygen is number 2, which is about 21%. So almost 99% of the atmosphere is run by two gases. If this were to ever change, our atmosphere would be very different. We, as humans, could potentially be very different if some of these gases changed. Then we have a lot of minor gases, okay? And some of these gases, which are very small, okay, do have a huge impact on our life on Earth. So the three gases that make up about 99.9% of the atmosphere, nitrogen is number 1, followed by oxygen, and then argon is very, very small. And then we have our other gases, carbon dioxide, helium, methane. These are very small gases, but they're also very important. Methane and carbon dioxide especially absorbs energy. So the more carbon dioxide we have in the atmosphere, the more energy it will absorb. And what will that lead to? A warming atmosphere. And that's one of the things scientists have been watching over the last several years, how much carbon dioxide and how much methane is increasing in our atmosphere. Because the higher the numbers, the warmer the Earth will be. Even though they're a very, very small percentage. You can see how small percentages these are. You do not need to know the actual percentage for the test. So just to let you know that. But these very small components, carbon dioxide, water vapor, and dust particles, play a huge role, okay? They're good absorbers of energy, okay? They can keep things warm. That's why at night when we have clouds, okay, we have absorbed energy. So more clouds at night will lead to warmer conditions. So we look at these two gases, nitrogen and oxygen, and then the small gas of argon, and then we have these very minute gases that make up only 0.03%, very, very small. Water vapor makes up about 4% by volume. And again, these are all absorbers of radiation in the atmosphere, which could warm the Earth. As we look at these gases in the atmosphere, you can see we have a lot of variable components. Water vapor by volume makes up around 4%. There's this little hidden heat that's in the atmosphere. And we also look at aerosols and ozone. So a lot of these invisible particles trap energy, makes the Earth warmer. So scientists are always looking at, are these numbers increasing over time? And one of the things that global warming has been talked about is the increase of carbon dioxide. And that's what scientists continue to track. How are these smaller components changing with time? One gas that's a good absorber, that is ozone. That's 3 oxygen molecules. The good news about ozone, it's about 10 to 50 kilometers above the Earth, and that absorbs incoming solar radiation. So that is above where the humans are. So it can block a lot of bad radiation coming down and hitting the Earth's surface. If we didn't have the ozone layer, it would be much hotter at the Earth's surface, more radiation, and that may lead to the potential of more cancer. So that's one of the reasons why some of the gases are actually good for the Earth. Ozone is one of them. It's 3 oxygen molecules that come together. It's very important because it blocks harmful UV radiation. This ozone layer is located in the stratosphere. So there are some good gases out there protecting the Earth. Now we're going to talk more about ozone in the stratosphere as we go through the end of chapter 1. So first thing about chapter 1 that you need to know is what gases make up the atmosphere. What are they, why they're important, and where are they located? The second thing that we're going to look at in chapter 1 is weather and climate. And while they have the same parameters, they are different in time frame. Weather is what's happening right now. Your current weather conditions. It's raining outside in Farmingdale right now. It's 78 degrees in Farmingdale right now. The low is going to be 50 degrees tomorrow. That's weather. It's happening right now and generally within the next 72 hours, or nowadays we talk about the next 7 days. Climate is an average over an extended period of time. What happened on this date, say the last 30 years? And that would give us an average and let us know what's happening. So scientists look at what happens over 30 years, 50 years, 100 years, thousands of years. We know our climate on Long Island. It snows in the winter. It gets hot in the summer. There's chance of thunderstorms and 100-degree heat, and also the threat of hurricanes. Why do we know this? Because over time, a lot of these things have occurred. And over the last 30 years, Long Island has seen an average of 30 to 40 inches of snow. So we do get a lot of snow here on Long Island. So that's climate. It's over an extended period of time. Weather is over the right now, a very short period of time. So there is a difference between weather and climate. Okay, same parameters, but over a different time period. And some of those parameters that we look at is air temperature, humidity, type and amount of cloudiness, type and amount of precipitation, air pressure, and the speed and the direction of the wind. These parameters will become more important as we go throughout the semester. An example of our climate would be our almanac. It tells us what happens on average over a specific date. You can see on this particular date, here's the normal or average high, the normal low, the record high, and the record low. So if you were to tell your friends, oh, if you're coming to Long Island in early September, it could be in the 90s because we have a record high of 92. It could be cool in the morning with a record low of 47. But typically it's comfortable where the average temperature is around 78 during the day and 63 at night. So these are the averages. Also, one of the things we'll look at is sunrise and sunset time. You'll notice sunset is going to get much shorter. It'll generally set around 4:25 in December. So towards the end of our class, sunset will be getting shorter, and we're going to talk about that in chapter 2, where the sun's rays hit, okay? So weather and climate. Climate's an average over time, okay? And you can see in January, here's an example, that on August 31st, the average high is 79, the average low is 62. That's an example of your climate, okay? As opposed to on August 31st, if it's going to be 83 degrees with showers and storms, that would be an example of weather. Weather is the day-to-day state of the atmosphere. Climate is over time. So if you're curious on what the weather will be, that's a forecast. But if you're curious on what the temperature should be around or what are the record highs and lows, these are your almanac pages which will let you know what we should be in September. We do get hot on Long Island and we do get very cold. The record low for Long Island is negative 23 degrees. So 23 degrees below zero back in January of 1961. We've had record highs. This is at Brookhaven National Lab where the temperature got up to 101. At Long Island Ice MacArthur Airport, we've seen a temperature up to 104 degrees. So we do get hot weather and we do get extremely cold weather here on Long Island. So again, climate, it's the average of those weather conditions to describe a place or a region. Weather is the day-to-day state of the atmosphere at a given time and place, pertains to short term, generally present to 72, but sometimes up to 7 days. All right, a couple of terms we need to know. Heat. Heat supplies the energy to drive the atmosphere, and we get that energy or that heat from the sun. Remember, the sun's rays are going to come in, and we're going to talk a lot more about that, how the sun's rays come into the atmosphere in Chapter 2. Moisture. Moisture supplies water for clouds and precipitation. Also supplies the energy by latent heat evaporation. That energy will help air to rise, to get the evaporation, to get the condensation, to get clouds and precipitation. Air pressure. Difference in air pressure causes wind. Wind is going to be very important for Long Island and in this class because a certain wind direction can give us a certain type of weather. We focus a whole chapter. Chapter 6 is about air pressure and wind. So remember, the differences in air pressure causes wind. The greater the difference in air pressure, the stronger the winds. So we'll be looking at that more in Chapter 6. And for an example, here's your current wind conditions, depending on when you're looking at Chapter 1. Now, this image right here we'll talk more about throughout the semester, but there's a lot of features that we're going to be looking at. The L is low pressure. The blue H is high pressure. High pressure and low pressure. Difference in pressure causes wind. The other features you see, these triangles, blue, these semicircles, red, those are fronts. We're going to talk about fronts in Chapter 9. The areas of green on this weather map shows rainfall. So this is basically a weather map that will show us weather conditions over the next 48 hours. And we'll talk more about in detail this later on. Something that is very important for Chapter 1 and right through your final, a radiosonde. A radiosonde is an extremely important piece of weather equipment. It tells you what's happening in the atmosphere above the ground. So a really important information gatherer. And what happens here is you have a weather balloon, and in this woman's hand, that is the radiosonde, which looks like this right here. That radiosonde will give us temperature, humidity, pressure, wind speed, and this information from the radiosonde goes into weather computers. So you hear about meteorologists talking about, oh, this weather computer says this weather computer says that. So I'll quickly pull that up. Let me see where I have that. So let me show you this real quick. So these are forecast weather models. Okay, this happens to be the GFS model, which is an American model. So that radiosonde, okay, the weather balloon goes up, it gathers information, it tells us what's happening above the ground, and then we get weather information like this. And this computer model goes out 16 days. So to give you an idea, this tells us, this happens to be September 11th. It is showing us that it may potentially rain on that day. And as I go forward, it'll give us an idea on when it's going to rain or not. So this one goes out to 10 days there. If I go back and look at some of the other numbers, the one model that I just showed you was not fully updated yet. It's loading as I speak, but forecast hour 384. So this will show us all the way up to September 18th, potentially. If there's going to be any hurricanes, any tropical systems, right now it's showing the potential of rain towards Monday, September 14th. So the radiosonde will help get this weather information out, and it shows all this information in the atmosphere on where air is rising, where air is sinking, where we as meteorologists can help forecast the weather. So that information comes from a radiosonde. Extremely important weather equipment. It lets us know what's happening above the ground. Very important, levels of the atmosphere. See figure 1.20, page 18. Thermal structure of the atmosphere, pages 16 to 20. Please read these pages. I'm going to give you a hint. They're going to be on the test and on the final. So you want to go over those images right there. So here are the diagrams also that you're going to be looking at. Different examples of the atmosphere and different layers in the atmosphere. I left this one with the letters so you can kind of guess what layer this is. What is layer D? What is letter C? What is layer B? What is letter A? And there's a couple of other images to give you an idea of what's happening in different portions of the atmosphere. Again, that is going to be on pages 16 to 20, okay? So please make sure you read those pages and look at these diagrams. Now, as you scroll down here, we're going to be looking at different layers in the atmosphere. There's a lot of different layers inside our atmosphere. The major ones we're going to talk about is the four major layers, okay? The troposphere, the stratosphere, the mesosphere, and the thermosphere. And these spheres are divided by pauses, which are also layers in the atmosphere. So what we're going to be looking at is what's important about each one of these layers, where are they located, and why are they important. So when you're looking at these charts here, you can see thermosphere, mesopause, mesosphere, stratopause, stratosphere, thermopause, and troposphere. So there's different layers inside our atmosphere, okay? And what happens with these layers, they're defined by their temperature and their chemical composition. So we're going to be looking at some of the things that are important inside these layers. So I'm going to click on this graphic right here, and we're going to start towards the bottom. This yellow line that is going up in the atmosphere, that is a temperature change with height. It gets cold, it gets warm, it gets cold, it gets warm. This decrease in temperature in the lowest layer of the atmosphere, this troposphere, is measured by the radiosonde. This temperature decrease is called the environmental lapse rate. The environmental lapse rate, okay? And in the troposphere, that temperature 99% of the time decreases with height. Then at the troposphere, it stays steady. Then in the stratosphere, it increases. It stays steady at the stratopause. It decreases in the mesosphere. It gets really cold until it stops. The coldest point in the atmosphere is the mesopause. At the mesopause, the temperature hits the lowest temperature in the atmosphere, then starts to decrease into the thermosphere, which is the warmest temperature in the atmosphere. So we're going to be looking at this temperature increase and decrease. Let me go back here real quick. So the temperature decrease in the tropopause, the bottom layer in which we live, is called the environmental lapse rate. The environmental lapse rate. This average rate is about 6.5 degrees Celsius per kilometer. So what happens here is, you see this little yellow line at the bottom in the troposphere? The temperature is decreasing, getting colder, decreasing with height, 6.5 degrees Celsius per 1,000 meters. So if you go up 1,000 meters, the temperature drops 6.5 degrees Celsius. You go up another 1,000 meters, the temperature drops again another 6.5 degrees Celsius. The one thing about this environmental lapse rate, it is not constant. We have an average value, but we need to measure it every day because it changes. We measure that environmental lapse rate through the radiosondes. That's why the radiosondes are extremely important, okay? And we have all these things that we can get an idea of the atmosphere as what we call stable or unstable. These are some of the things that we're going to look at in chapter 4. Chapter 4 is the hardest chapter in the book. And we're going to talk more about the environmental lapse rate, radiosondes, what we call soundings here. We're going to be looking at the stability levels when we get into chapter 4. But right now, what you need to know is the environmental lapse rate is not constant, and it is measured by the radiosonde. The average value of the environmental lapse rate, it decreases by 6.5 degrees Celsius per kilometer, or 1,000 meters in the atmosphere as you go up in the troposphere. Sometimes, though, I said 99% of the time temperature decreases. Sometimes it actually increases. A temperature inversion is where temperature increases with height. And when you have an increase with height, the atmosphere actually becomes stable. Decrease in height, it becomes unstable. So that's one of the things we'll be looking at. The greater the temperature drop, that greater the temperature decrease, the more unstable. What does unstable mean to you? More clouds, thunderstorms, heavy rain, heavy snow. That's what we're going to be looking at in other chapters. but to generally give you an idea, if the temperature decreases with height, you have unstable air. If the temperature increases with height, you have stable air. The troposphere is known as the weather sphere. This is where all important weather phenomenon occurs, in the weather sphere, which is the lowest layer of the atmosphere. Okay, that is our troposphere, also known as the weather sphere. So down here, here's Mount Everest. So generally under about 30 to 40,000 feet, that's where the troposphere is. That's where we have all of our weather phenomenon. Okay, generally think about where the planes fly and lower. If you ever flown in a commercial jet, that's where they fly, anywhere from about 30 to 38,000 feet. So lower than that, that is generally where all the weather occurs. Okay, now once we get to the tropopause, temperature starts to remain steady and then will increase in the stratosphere. And the reason why we have the temperature increase in the stratosphere is because of ozone. So the stratosphere, the boundary between the troposphere and the stratosphere, that is the pause. So once we pass the pause where we have a steady temperature and the temperature starts to increase, you have ozone, which absorbs incoming solar radiation. So this is why you have a temperature increase. Okay, so the temperature will increase in the stratosphere because of the absorption of ultraviolet radiation from the ozone layer. Now, once we go a little bit higher, again, at the tropopause, we have a constant temperature once again, and then in the mesosphere, the temperature really starts to decrease. In the mesosphere, really not much going on. Temperature decreases with height until the mesopause. The mesopause is the coldest layer in the atmosphere. Okay, it hits the coldest temperature, and then it starts to interact with the next layer above it, which is going towards the thermosphere, and that's why things start to warm up again. So in the mesosphere, temperature decreases all the way to the mesopause. The mesopause is the coldest layer, and in the thermosphere, the temperature starts to increase. Okay, so the mesopause is the coldest. The thermosphere, there's no upper limit to it, but it's the hottest layer. The temperature getting up to 1,000 degrees Celsius or 1,800 degrees Fahrenheit. That is really, really, really hot. You have ratified air moving around. Think of kind of outer space, okay? Incoming solar radiation comes in, it hits that air and really heats it up. So it can get up to about 1,800 degrees Fahrenheit. Now, inside the thermosphere, okay, it's not throughout the entire thermosphere, but a small layer inside the thermosphere, we have the ionosphere. So it's its own layer inside another layer. And the reason why the ionosphere is not in the entire thermosphere, because there's a little bit of electrical charge layer. And this is the ionosphere. So the ions are heated up from the incoming solar radiation, the shortwave solar radiation from the sun. And with that, it heats it up very, very rapidly, and we get a lot of high energy. And inside this ionosphere, with all this high energy, we get what we call the auroras, or the northern borealis, or the aurora borealis, or the northern lights. Okay, the auroras take place in the ionosphere in this electrical charge layer. So the auroras only occur in the ionosphere. Even though the ionosphere is in the thermosphere, they only occur in the ionosphere where we have all these electrical charged things going on. The aurora borealis is the northern lights. The aurora australis is the southern lights. Southern hemisphere versus northern hemisphere. And this is kind of what the northern lights look like. And you can check out the aurora page and check out some more images on the Wikipedia. So that's kind of it of chapter 1. The takeaway, the focus here is layers in the atmosphere. What's important about each one? Is the temperature increasing or is the temperature decreasing? In the troposphere, we have oxygen, we have nitrogen, and the temperature is decreasing. We also have carbon dioxide. We have all those smaller components of gases, water vapor, which is 4% by volume. We also have dust particles, when we also have carbon dioxide. So those kind of play a role in our climate and our weather. So what's happening near the Earth? It's the weather sphere, all these different things that are occurring. So know the levels of the atmosphere. What's important about each level? What makes one different from the next? Air temperature, gases, location. Climate and weather, are they different? How are they different? Okay, your almanac gives you an idea of the climate of the area. It'll give you an average over many, many years of what the weather was on that date. Now for chapter 2, we're going to talk about seasons. Daylight. Why do we have seasons? Where are the sun's rays hitting the earth? What are the dates of the season? Heat transfers. Why is the sky blue? Why is sunsets red? Albedo and wavelength. So that's for chapter 2. So you can already see I'm giving you an idea of what potentially there will be on test 1. So go through chapter 1. If you have any questions, let me know. Okay, read chapter 1 in the book. And also what you're going to notice, if I have any diagrams or something that's very important, you're going to see levels of the atmosphere here. Figure, page number, pages 16 to 20. So I'm going to help guide you on where you should focus your studying. And when you're studying, you watch these videos, you read the textbook, and you look at the class notes.